Okay, so it's a pleasure today that we'll get to hear from a PI of a mission under construction, and there are not that many UV missions, so it's always good to hear the next one. Evgenya Shkolnik from Arizona State University. She's a professor in the School of Earth and Space Exploration at ASU. She obtained her MSc and PhD at the University of British Columbia in Canada, and her thesis was titled Chromospheric Activity Induced by Short Period Planets, a search for modulation of calcium H and K emission. Evgenia was a Carnegie Fellow at the Department of Terrestrial Magnetism, the Carnegie Institution in Washington, D.C., and an NRC Fellow at...
You never put up your hooks, sweetie, but we can talk about that, like where you want.
Okay. Sorry. Okay, so and NRC Fellow at University of Hawaii before joining the Lovell Observatory. In 2015, she moved down south to Tempe, joining the School of Earth and Space Exploration. She's got a wide range of interests. Star-planet interactions as a probe of planetary and stellar magnetospheres, effects of stellar radiation on formation, evolution, and habitability of planets, search for and characterization of disks and planets around young M dwarfs, gas emission from planetary atmosphere and debris disks, and most relevant to this series, keen interest in small satellites and CubeSats for astrophysics. She's the principal investigator of the Star Planet Activity Research CubeSat, otherwise known as SPARCS, and we'll hear quite a bit about that during this talk. Welcome to the UV Club, Evgenia, and it's all yours.
Great. Thank you so much, Sri, for the invitation to come speak, but also for organizing this whole UV Club. The few that I've been able to attend have been very interesting and dynamic and with great conversation. So I really appreciate that you're doing this. It's great to see everyone, even if it's just your names. I wish we could all be together someday soon. Okay, so I'm going to try and finish up a bit early so we could have some conversations before the top of the hour. And so let's see, let's get cracking. So I'm going to tell you about both SPARCS, but also UV Scope. UV Scope is a mid-X concept that we are developing with JPL. Now I'm the PI of that as well, and that's going in for the December deadline coming up. And so I'm here representing the HAZMAT team, which I'll discuss, the SPARCS mission team, and the UV Scope team. So it's a lot of people, and you'll see their names throughout. So let's just make sure we set the tone here of what we're trying to do, what I am trying to do, as far as like the bigger picture of contributions to science, and that is really addressing what I think are the biggest questions in exoplanet science today, right? So we know that Kepler has shown us that planets are ubiquitous. In fact, there are probably more planets than there are stars in our galaxy. And as such, just looking for planets anymore isn't really the goal. We know they're there, but now we have to look for planets that we can characterize, which is the goal of the TESS mission. And in order to answer the big questions right now in exoplanet science, which is how do they form? How do planets evolve? What are they made of? And of course, the age-old question of, are we alone? And I know you guys who are fans of the UV will be pleased to know that UV data does provide critical information that we need to answer all of these questions. So that has been a big part of what I'm focusing on for the last decade, really.
Yeah, I don't know what you're talking about.
Thank you for muting. So I've been focusing over the last decade on studying the UV radiation environment of these exoplanets for all these reasons. So I'm going to cover today why UV matters in exoplanetary systems, and to convince you in case you're not convinced yet, tell you what we've learned from the existing data that we have with the GALAX archive and new data from HST, And then given the limitations of the existing data, why I and my team are motivated to build new instrumentation, because there's so much to learn and we just cannot do it with the existing data and the existing facilities. So very briefly, just to make sure, I know we have a diverse scientific crowd here with different interests. So I just wanted to back up and just say a little bit about what why the M stars, these low mass stars, are really very exciting. And it's not just because they are smaller and make the planets more detectable. So some people say we're looking for habitable zone planets around M stars because they're easier to detect. That is true, that's a bonus. But in fact, we're looking for planets around M stars, or habitable planets and small planets around M stars, because they are the most dominant stars in our galaxy. 75% of the stars in our galaxy are M stars. And if you work out the statistics, it turns out that most of the habitable zone rocky planets orbit M stars in our galaxy, and that is about 50 to 70 billion habitable zone rocky planets in and around M stars. And so the value of the M star is really critical. And so what we do, one thing this plot on the right hand shows you is that when we say the word M star, or the phrase M stars or M dwarfs, we're not really being specific enough, because they span 3 orders of magnitude in luminosity. And therefore, throughout this talk, you'll hear me say early M's, mid M's, and late M's, because they are fundamentally different kinds of stars with different characteristics and different UV emission and evolution. Okay, if anyone has any questions, by all means, chime in. I think we're a casual, friendly crowd here. And so you might have heard of Proxima Centauri, of course, our fabulous nearest stellar neighbor, which hosts a rocky planet in its habitable zone. And it's only 0.2% of the solar luminosity. And what that means is that the planet is very close to its central star to be in the habitable zone. And here is an image using a solar eclipse image where I've put a Proxima b at where it would be. So if you imagine that this is now not the sun, but actually Proxima b, a much smaller star, and you put its planet in the habitable zone, you're only about 10 stellar radii away. So this is very different, right? We're very comfortable at our 1 AU position. And this planet may not be so comfortable, I guess is the point. And we're trying to figure out how comfortable it really is. So the consequences on the planet at such close distances, due to the high energy radiation, environment, is that you could have atmospheric heating and escape by extreme UV photons, which are very hard to observe well, at the moment, we can't observe them for any stars other than our sun, but even if we did have such a mission, you can't observe them for the vast majority of exoplanetary systems because of the ISM absorption. But we need to figure out what is happening in the extreme UV also, because of this atmospheric escape problem, which could blow off the atmosphere completely. Also, we really need to understand the atmospheric photochemistry, and that is affected by the far UV and the near UV. And of course, whether the atmosphere is there and its chemistry affects surface habitability. And in addition to that, it affects also the detection of its habitability. So if we're looking for biosignatures, the UV has this clever way of producing both false positives and false negatives of biosignatures that we would be looking for. So in general, understanding the UV is really critical. I hope I've convinced you. I'll show you a few more plots in case I haven't. But here's one example from Sarah Rugheimer's work from 2015, where she shows that you could take the same Earth-like atmosphere around the sun, and you see the spectrum in black. You put it now in the habitable zone of an inactive M star, which is the green curve here. And you would see this reflectance spectrum. It's a model of reflectance spectrum off the habitable zone planet. And if that exact same planet is in the habitable zone of an active M star, you would get a completely different spectrum of the planet. And you would interpret, in this case, the oxygen and the water abundance very differently for the exact same planet. As we said about planet atmospheric evolution, you could also see how these are beautiful models done by John McCann and Ruth Marie Clay and collaborators, where you can now see through these models, at least, right, that different stellar environments will produce different atmospheric responses and even tails. And this has been something that we have observed with HST. is long Lyman alpha tails because of this kind of process with an interaction with its central star. Now, part of the HAZMAT program is not just collecting observations, which I'll show you in a minute, but is also building an entire new grid of upper atmosphere models. And the reason why this is important for low mass stars is because you see in this red curve here, this is the state-of-the-art stellar models for M stars. This is the Phoenix models. You've probably heard them all, you may have even used them all, but you see that they completely underestimate the UV across the entire wavelength range by orders of magnitude. And the reason for that is not because they're bad models. They're actually excellent models, but they're created to only reproduce the photospheres, right? But we know that the UV is coming from the chromosphere, the transition region, and the coronae of these stars. And so we are now working to build, essentially, the upper atmospheres of these stars onto the photospheres so that we can then predict out the far UV and near UV and the EUV. So they're semi-empirical models in that we use our far UV, near UV data that we actually can get from HST, the spectroscopy we get from HST, and predict what's happening in the EUV. And the early results are already published by Sarah Peacock. And you can even get the spectra, if you're interested, they're on the MAST website for download, if you're curious about that. Okay, so the whole goal of this HAZMAT project, in addition to these models from the data perspective, is to map the UV evolution across time and across stellar mass, focusing on Ks and M stars, because these are the most dominant, and they're the ones for all the reasons that I spoke about, why we really care about what's happening in the planetary systems around these masses. So we used archived photometry from GALEX, and we have new far UV and near UV spectroscopy from HST for this program. So I know many of you are probably very familiar with GALEX, but just to briefly catch you up, it surveyed about 2/3 of the sky in two bands, these NUV and far UV, and has left us with a really beautiful archive with limited repeated observations for stars. But because of the large field of view, right, there are many stars to study. So we could start doing statistical studies with GALEX, even if we don't have the time domain covered with it. It was beautiful use of that data. And here's just one example of a flare where there was ample time resolution to observe it. Here is an M4, so this is now a mid-M in our range of M's, and you can see that it increased by 10 UV magnitudes, or a factor of 9,000 in just 200 seconds. So you could look at the photon. So even though most of the images there are about 300 seconds, you could look at them with higher time resolution. So that's pretty remarkable. I can show you more examples of that in a minute. What we could do with GALEX, though, in the few that did happen to have multiple observations, not with the same time resolution, is look for variability across the entire mission. And so what we were able to tease out in this plot here is that indeed, the stars vary more as they get smaller and smaller. So the later spectral types, you have more relative variability in both band passes. So being able to quantify this has been really helpful in designing the photometric requirements of the SPARCS mission, which Sri mentioned, and I'll go into more detail in a bit. And then if you take a bunch of years of work and graduate student thesis and a postdoc or two and put it all together into one slide for the HAZMAT program using GALEX, we were able to look at the evolution across time as a function of stellar mass binning by early K, early M, and late M. And what you're seeing here is that we can now say from a statistical standpoint what planets were exposed to at the time of formation, early on in their history, and then later on as their atmospheres evolve, or if they're blown off after their secondary atmospheres are there, as the Earth is currently on its secondary atmosphere, and potentially if life were evolving on this planet, what is the environment? And you can see here that the late M's, the red curve, stays more active for longer, and in the habitable zone, the planets will just see more UV radiation. One thing that was surprising actually about this work is where the early K's come in, right? So people have been talking about M stars being all flary and causing all this trouble, right? Well, maybe Ks are super habitable. You might have heard this term already, and there was a lot of hope for looking for habitable zone planets and characterizing them around K stars. But our work here using GALAX has shown that K stars are really not that different from M stars. They're probably closer in M being M-like than G-like. And that's what this work showed, which means we may have to reconsider what superhabitable really means for a K star. And then the HST program of the HAZMAT program, and now the HAZCAT program, because we've just finished up the same idea, but for K stars. Here are my wonderful collaborators on the right-hand side. And this program has had over 209 orbits, even more now. I need to update that. So a lot of HST time, a lot of grant money, a lot of effort in order to understand these really important problems. So I really appreciate now that the community understands that we need to characterize the UV for all these stars, and HST is our current workhorse for that. So here's just an example of the spectra we've collected. Work is led by Park Lloyd, a postdoc in my group, and you can see here the difference. You have UV emission, it's the spectrum here of different age stars, and it's just a representative star, a 40 million year old star, which is part of the Tuck-Hoare moving group. For those of you who might care, and then the Hyades star at 650 million years, and then a field star. And you could see that they differ by orders of magnitude across these wavelengths. But I would refer you to the paper for more details on that. But one thing that comes out of all those data is flares or flares. And here's just an example of the range of flares that we have detected in the far UV with HST in just 10 hours. This particular plot is just showing you 10 hours of HST observations. There are actually more flares detected. This is just all the ones I wanted to squeeze onto a plot. And we have another 10 flares in just the K stars also that are yet to be published that my student is working on. But this one in the top left is really interesting because it's really strong. It is in fact the strongest flare ever detected by HST on an M star. And we dubbed it the HAZ flare, named after the HAZMAT project. And it turns out that this flare happens every day. This kind of flare happens every day on a young M star. In this case, it's an early M star. And you can see that it's increased by almost a factor of 200 in over 200 seconds. So that's for young stars. So then you think, okay, well, old stars are not going to be that bad. Well, here's a recent result from our group led by Meredith McGregor, where we looked at HST far UV spectroscopy simultaneously with TESS optical photometry and also with ULMA and some other wavelength bands as well. It's a very nice paper showing a single flare observed in many different wavelengths, and there's lots to learn in this kind of multi-wavelength observations. But here's just an example. Here's Proxima Centauri. It's an old star, rotation period of 83 days, something that you would hope would not be quite as flary. And if that's not a word, it should be. But you can see that this one flare increased the far UV continuum by a factor of 14,000. Right? And the lines increased by a factor of 3,000, while at the same time, the TESS optical light curve increased by only a factor of 10.
Evgenya, can I ask you about this for just a second?
Yeah.
I mean, if the stated goal here is to really look for habitable planets, I mean, looking at this diagram, it would be very unlikely that these would be habitable in any way. So why, I know this is an old argument, but why are we concentrating so strongly on the M stars when they look like this?
Okay, thank you, Harvey, for that. Okay, a few responses there. We don't know yet exactly what this does to the planet atmosphere. That is we're still collecting the data to inform the planet modelers. So we work in collaboration with VPL, the Virtual Planet Laboratory, led by Vicky Meadows, where we are then giving her and her team more accurate UV data in order to simulate what's happening on the planet atmosphere. And so, in fact, people haven't really tested what the effect is on the planets just yet. You're right, this could be kind of scary, but maybe not. I mean, depends on the composition of the planet. and also what the star is doing. If you're also worried about particles, which you should be, because particles will also have an effect on the planet, there we have to consider what the magnetic field of the planet is and how that interacts with the particles. And but one should not assume that a magnetic field protects the atmosphere from particles. That we say that a lot, but that's in fact not been proven at all. So why we care, I guess for me personally, why I care is because part of my career's goals is to understand the distribution of habitable environments in our galaxy, and most of them are around M stars. So if we show that no M star planet could have an atmosphere, we have not shown yet, but if we show that, then we understand that the distribution of life is much narrower than we think, or than we hope.
Thanks.
Okay, great. All right, so zooming in on the Has flare now spectroscopically, another thing I wanted to point out was that you have this black body continuum that is in fact hotter than we typically assume. Usually in our field, we've been assuming 9,000 Kelvin black bodies that are associated with large flares. But here we're detecting a 15,000 Kelvin black body. And when you zoom out on the wavelength scale, this is what it looks like. The spectra during quiescence are in blue, then in orange is the flare, and then you can fit this very hot black body. Similarly, Cynthia Froning published a 40,000 Kelvin detection of a black body from an M-dwarf flare using HST. So what the point of this particular plot is to say, we don't actually know what the total UV emission is upon a planet, and we just need more data. And here exactly, this is also showing you a similar kind of idea now using the statistics that we have from HST, showing you what we call a flare frequency distribution. And you can see how sun-like stars are on the green line here, roughly. The old M stars lie on the blue line here, where you're looking at the frequency of flares as a function of energy. And the orange is the young M stars anchored by the one Has flare, which happens roughly once per day, but we don't know what's happening in this once per month or once per year range. Clearly this line cannot extend forever. It has to turn over at some point. And where does that actually happen? And what are the energies of those flares? So I can quickly pause for it. That's kind of the science motivation before I get into SPARCS and UV scope. If there are questions particularly about the science thus far, I know. You all good? Okay. All right. So one mission, so in order to get to this kind of monitoring program where you could stare at a star for a month at a time, which is clearly not feasible with HST, is we decided to build SPARCS, to propose SPARCS to the APRA program at NASA. And it's now halfway through development, and that's very exciting, building that. Now, we already have our telescope. It's sitting in the lab at ASU. It's a 6U CubeSat, which is like this big, with a 9-centimeter telescope. And the goal is to be a hitchhiker, essentially, into a sun-synchronous orbit. And the plan for this, the plan is to observe in the far UV and near UV simultaneously, so we can get these flare colors of a sample of M stars with a range of ages. And as I showed you before, these M stars vary, by many percent, and even more so in the UV. And so our photometric requirements are not, millimag photometry, right? We just need 1 to 10%. And so that is our plan for SPARCS. And these are our collaborators. This is in collaboration with JPL and many other science team members from all over. And kind of the secret sauce of why we can do good science in a 9-centimeter telescope is because we have, we'll be using these delta doped CCDs that JPL has developed that are more sensitive, much more sensitive, 5 to 7 times more sensitive than the GALEX detectors. So even though our mirror size is relatively small compared to GALEX is at 50 centimeters, we're at 9 centimeters, we're really buying back some of that real estate with good detectors and high throughput filters as well. And the bands are designed to cover emission features that we care about for the M stars, so chromospheric and transition region features. So there, so that was the motivation in selecting those particular wavelength ranges. And here I'm showing you kind of a simulated what we expect to see for a given star. This is a 30-day monitoring of an M star, and we should see in the top panel here, let me find my mouse, we should catch a bunch of flares. They should be very strong, and this in normalized flux we could reach up to, you know, like a factor of 1,000, 2,000, 4,000. We don't like really even know, to be honest. Based on what we've seen with Proxima Centauri, it could be even stronger than what I'm showing you now for the rarest of flares. And we'll also monitor the rotational modulation in the UV. So we should be able to get understand the rotation period, and which we'll know ahead of time, but see what the actual modulation is at those wavelengths. And as a comparison, the longest HST stare was for that Proxima Centauri program, which was 36 hours. So that's the longest HST has looked at a single target. And even if you add up all the HST time on M stars, it doesn't span this entire range. And so we're really probing a time domain, time range that you just cannot do with HST, and you need dedicated facilities for. Okay, so this is one of the challenges. I told you that we don't really know how strong these flares will end up being. And they could be so strong that they could A, saturate our detector, and B, we might not resolve the whole flare because our integration times during quiescence might be too long. And so one of our postdocs, Tahina Rami-Ramonsawa, wrote some clever software that will be onboard dynamic image exposure software, where you could control the exposure times of your observation, depending on what the star is doing. And so if a sharp rise is detected, the exposure times will immediately shrink. You will still gain the signal to noise thanks to the flare, but you will also be able to trace out the flare. And this is, I believe, the first time that this kind of software will be flying up in space, this kind of automated dynamic exposure control. And he just submitted a paper to PASP on that. And so if anyone is interested in reading more about this very useful software, especially for flare work, do let me know, and I'm happy to pass it around. Okay, so putting SPARCS into the scientific context, and really it's not just SPARCS, I think it's also going to be UV scope and any future UV observations that I know people on the call are planning, is that we observe the star, we measure the light curve of the star, so we would measure both the rotational modulation and flares, and then we would use those data to build new upper atmosphere stellar models, which we're already doing with HST data, but we will have more, and we will fill out the whole grid that we're interested in stellar mass and age. And then we can apply those data to planetary spectrum. So as I mentioned, Harvey, people have not had the data in order to model the planet atmospheres with any accuracy. So that's what part of all this work is to do, is to supply the modelers the correct data. And then those can be compared with terrestrial planet atmospheres that we're going to be observing, hopefully with JWST, but probably with, perhaps even with the next flagship, or even from the ground with the ELTs. And then we'll be able to, at least for the terrestrial habitable zone planets, be able to distinguish what the probability of our false positive or false negative detections might be. So we are aiming for a 2023 launch, and we're about halfway there, and we're very excited about that. And moving on to something further into the future, I wanted to tell you about UV scope, which is the ultraviolet spectroscopic characterization of planets and their environments. So it falls in the same theme of trying to understand the environments of exoplanets in the UV, but now with more targets, of course, now with spectroscopy and not just photometry, and also with different driving science cases. Let's see. The mission will be directly probing planetary atmospheres through transmission spectroscopy. So I expect you probably know what that is, but as the transiting planet orbits in front of the star, you'll see the constituents of its atmosphere. But in this case, this has been the classic way to study exoplanet atmospheres in optical and infrared wavelengths to date. But now we're going to do it in the UV, something that has not been done much. It's done a little bit with HST, but has not been done much for planets. And so this is really, I think, very exciting. And so all our targets are known transiting planets, both large and small, across a wide range of stars, A, F, G, K, and of course the M stars that are going to be of interest to JWST and potentially future flagships and so on. So as you probably are aware, though, that the photons from the star are being absorbed and are impacting different levels of the planetary atmosphere. So the UV scope mission will essentially be characterizing the three main layers of an exoplanet atmosphere. So it's the uppermost layer, right, which is heated by this extreme UV radiation. But how do we really measure the mass loss induced by that, right? And so we will be doing NUV and FUV transits of the population of small planets in order to look for the escaping hydrogen through Lyman alpha and other metals. And we really want to answer the question, how much mass is being lost to space, right, across the diverse population. In the upper atmosphere here, or some people call it the middle atmosphere, but this region of the 1 millibar to 1 nanobar, will also have NUV and FUV transits, as all our targets will, in order to answer the question of what roles do upper atmospheric properties play in the escape processes, but also determine the composition at this layer. And that also tells us about potential rainout of other molecules, and that informs then cloud formation at the lower levels, right? And this is where some spectra have been shown, some transmission spectra in the infrared have been very, very flat, probably due to clouds. And so we need to understand cloud formation down in the lower level, but that is controlled by this middle atmosphere. And the lower atmosphere is already well probed by optical and infrared. So we will not be doing transmission spectroscopy, or at least our driving science cases. We might detect exospheres, exospheres of small planets, but and maybe understand terrestrial planets this way. But generally, the lower atmosphere is observed well at other wavelengths. However, as I had mentioned in the beginning of the talk, right, it's the UV inputs that really affects the photochemistry of the lower atmosphere. And to do that, we will be doing a monitoring campaign of the radiation environments. So we will measure the NUV and FUV spectroscopy. We will use our current techniques to predict the EUV, which is, as I mentioned, not observable for the vast majority of exoplanet hosts, including the transiting ones. And so this way, the entire mission looks at the different layers of the atmospheres and how they're completely interconnected within the context of their stellar host. So the Lyman alpha case studying the exosphere here is essentially to understand this plot, which you've probably seen. This is called the radius valley or the radius gap. And it's a fabulous, I think, a fabulous result from the Kepler mission that showed that these small planets, those that are about 4 Earth radii or smaller, actually come in 2 sizes, which I don't think many people expected, although it was predicted in 2013 by Owen and Wu. But still, to understand what the driving mechanism of that requires a dedicated suite of observations in Lyman alpha. And so that's part of our driving science case. And as I mentioned before, HST has been a great pathfinder for this kind of work, actually for all of the work that UVscope and SPARCS is planning. HST has been just so great to tell us how important this is and how much more data we really actually need. And so here's just an example of one of the first Lyman alpha transits observed around GJ 436. And you can see that there's a nice clear tail of current mass loss going on. In this middle or upper atmosphere, this here I'm showing you model transmission spectra of hot Jupiters. So this is not the star, this is the planet. So this is what we expect to see in the UV, and the transit depths are much bigger in the UV because of the cross sections of particular elements here. In particular, it's the silicon oxide over here and an iron molecule here. And so we will be studying these in order to understand the condensation and cloud formation in lower atmospheres. And in the lower atmosphere of terrestrial planets, here's an example. I mentioned that we work with VPL, Virtual Planet Laboratory, where Evan Davis, who's a student of Vicki Meadows at the University of Washington, produced this really interesting plot where he took some hazmat spectra. So you could see across here, the colors are ages going from 650 million years to 1 gigayear, 3 gigayears, and so on. But as the stellar UV evolution, as the UV emission declines with age, the photochemical impacts are observable in the planet spectrum, right? So here's kind of a full spectrum here, zoomed in. But one thing that really stands out is this O3 feature, which people are looking forward to using as a biosignature, but you can see how we can have a very clear false positive just based on the whatever the UV emission is of that star. And so this, I think, really motivates the need for characterizing the star. And so it's very interesting. And this is just, like I said, this is just the beginnings of the models. We have not explored all possible parameter spaces from the modeling standpoint of the planets. So that is all work that is going on right now. And then back to the flares, something that's very close to my heart here, looking at this plot again and trying to understand the true UV energy, right? And to get the full spectrum of the flare, not just the lines, but also the continuum, UV scope will get this entire range simultaneously. So we'll get all the way from Lyman alpha to 400 nanometers all in one shot for every star and monitoring multiple. So we'll have observations both during transit and of course out of transit for every target. And a simulated spectrum, what will UV scope spectra look like? It'll be kind of like this. We'll have a high resolution channel in the far UV and then a low resolution channel in the near UV. The plan is to have a 60 centimeter telescope and using these wonderful high QE delta dope detectors. And again, looking at transiting planets. Every target has a transiting planet, which is very exciting that we know so many that we can observe and do all these statistical studies. So just to summarize, I just want to say that if you have more questions or more interest, and hopefully I've motivated why we need the UV, but I know that I'm preaching to the converted here, as often we are in this group. And I gave you a summary of GALAX and HST observations, and if you guys want to talk more about that, I'm happy to dive more deeply into that. And then SPARCS and UV scope are, at least for this kind of research, I think our future at the moment, but there's so much to do. And so I'm totally happy to answer any questions. Hopefully I've left enough time before the top of the hour for good discussion. So thank you.
Thanks very much for the talk. Now we'll go through Q&A, and the easiest would be if you raise your hand, and for those who don't know, it's, I believe, in the reaction button at the bottom bar of your Zoom. And after your question has been answered, do lower your hand, otherwise I'll think you have another question to ask. So we'll start off with Fiona Harrison.
Hi, Fiona.
Hi, how are you doing? So great talk. That was very interesting. I do have, it's not my field, but, when I think of the sun, I think of the greatest threat to Earth's habitability being coronal mass ejections, as opposed to the sort of flares that happen in the, outer regions of the corona. I'm just wondering, what's the best understanding we have about CMEs on these smaller stars, and how do you detect them and determine what it is a CME?
Oh my gosh. Okay, I'm going to try and keep it short, but I have lots to say on this topic, even though I have no data to really share. I think you're absolutely right. It's really important. It's a huge gap. We know for the sun that the CMEs do correlate with their X-ray data. So, we don't know what those correlations are for M-stars yet. And we're working on that. People are working on that. There's been one claim detection of a CME on a star based on X-ray velocity variations with time. That was a paper. I can send you the paper, but I think it was from 2018. I'm sorry, I'm blanking on the first author's last name, but there's really not very much. I mean, people are trying to do this in the radio. So the radio could trace particles along the stellar magnetic field lines. And there's a big effort to monitor low mass stars in the radio. And in some cases, the radio as well as simultaneous optical, which would be great because then you could see potentially a flare in the optical and maybe see, some time delayed particle flux going on, being emitted. There's another technique called coronal mass ejection. No, sorry, it's called coronal dimming. And this is something the sun does, but has never been observed on another star yet. And what that is that when there's a CME on the sun, it actually blows a bunch of the plasma off the corona, and you end up with a hole in the corona for a little while. And then so the light curve of the sun, I don't have a whiteboard here. It looks like this. You have like kind of some baseline, then you have a huge flare, and it actually drops below the baseline and keeps on going while the corona refills. So that's another way that we're thinking about looking for CMEs on other stars.
So is the idea that the X-rays come from like fluorescence, or is it non-thermal emission somehow?
Yeah, it's non-thermal emission during the flare. And the X-rays do tend to correlate with the UV. So it's all part of the same magnetic phenomenon on the star.
So what you'd really like is a radio telescope monitoring your SPARCS star simultaneously with the UV, and then you could maybe.
All of it, yeah. So part of the SPARCS plan is to publish our observing program on the website as soon as we know exactly dates and times, so that people can try and get simultaneous H-alpha data, optical data, the radio observations. I think, yes, 100%, that's the plan.
Evgenia, right, before I forget, a colleague, you probably know Greg Hallinan, who's a professor at Caltech. He's finishing now the long wavelength array phase 2, which will have great sensitivity, roughly, I would say, well, it's the ionospheric cutoff. Let's say something like 20 megahertz to below TV band, or maybe 80 megahertz. And the good news is that he's really doing an all sky imaging survey. So the data will be there. So maybe you want to talk to him to follow up this idea that Fiona suggested.
He and I talk all the time, Shri. He's the guy I was thinking about actually when Fiona asked, because he's also building an optical photometer to do simultaneous radio with, his tagline for the LWA is all sky all the time.
Right.
Which is fantastic. Yeah.
And in the southern hemisphere, you have MWA, which also has it's not as large field of view as LWA, but substantial. So you may get, some of those things.
Right. And there's a big monitoring program also with LOFAR too, at the lower frequency range.
Well, the main thing is that they may not necessarily have the big field of view to do your simultaneous one, which is what Fiona was suggesting. So I was trying to look at something where you get it at low cost. Okay, I see a question from Shri Kulkarni, but at DESI.
Yes, thank you. Yeah, I'm a beginner in this area of research. Yes, I have a short question. You have shown in one of the slide the planet and different kind of three emission of UV in different wavelengths.
Mm-hmm.
Is it a planet of the M star? Is it is the structure is same for all the different kind of stars? I mean, if a planet have if it has a planet, the same structure, or is emitting the same thing, or depends on the atmosphere? How
You're
it
talking
is?
about that, you're talking about that onion plot?
Yeah.
Let me see. Let me see if I can find it for you. 1 second. This one?
Yes.
Right, no, they wouldn't have the same structure. This is just a, cartoon of roughly what we're talking about, but the pressures are there. The pressures of where so the exosphere is at this very, very low pressure. So no matter what planet you're looking at, it's at these low pressures that you would expect escape from. So this is just a cartoon to be representative of it. But if you see like Lyman alpha tails, that's definitely coming from the exosphere, no matter what size the planet is.
Are you comparing Earth data with other planets, or how you are calibrating the instrument?
I'm sorry, can you say that again?
How you are calibrating the instruments for these kind of measurements? Is it
Oh,
on?
calibration is its own separate story, specific of it, but we do have HST data, right? So we do have data at UV wavelengths that we are using to guide our knowledge to plan forward. Yeah.
I see. Okay, thank you.
Probably in that regard, Evgenia, you'd probably look at some bright, hot white dwarfs. We really do understand their atmospheres very well.
Oh, right. You mean for absolute flux calibration, right?
Well, yeah.
Yeah, for sure. SPARCS also. We also are going to use the white dwarfs.
Yeah, that's sort of like they're like amazingly well understood objects. Of course, whether they have chromosphere or not, that would be very interesting to discover in itself. But so either way you get, if you observe white dwarf, you can write a paper. In one case, it'll be AppJ supplement, the other case is a Nature paper. So
okay.
Okay, Amit.
Hello, thank you for the talk. I'm pretty new to this field, and my question is, you did mention something about finding whether the atmosphere that the particular exoplanet has orbiting the host star is whether if it's a first or second atmosphere, right?
Well, I guess we can make a statement about that if we expect that stellar type should have blown off the original primordial atmosphere in its first 100 million years. And then if it has an atmosphere now, if we're looking at an old stellar system and the planet is old and it still has an atmosphere, then we can deduce it's probably a second atmosphere because it should have lost the first atmosphere based on the evolution studies, right? Although we do have targets that are young, so we will be looking also at young transiting systems. There are just not that many young transiting planets known right now, and certainly not small young transiting planets. Those are really hard to detect.
The follow-up I had to that was with only the UV data that you have, how far and how solidly can we construct the atmosphere models?
Sorry?
How far in the history of that particular exoplanet can we construct the atmosphere models?
The atmosphere models, how far into the history of the planet?
Yes, how far back in time? Like, can we say that so and so had happened? That's why its current state is like this. I don't know the particular terms.
We can do it statistically, right? Because of course we can't stare at these stars, at these systems for billions of years, but we can look at what stars of that same mass, right, have been doing or were doing in their youth by looking at very young stars. And that's a big motivation for looking at stars of different ages, so that we can then say, from a probabilistic standpoint, what that planet was exposed to early on in its life.
Okay.
The goal is to be able to understand the full life cycle of the planet's atmosphere. We just can't stare at it long enough, right? So we have to use statistics to do that.
Thank you.
Okay, Boris.
Evgenia, thanks a lot for the lucid presentation. But still, I have a question really, to status of UV scope. You mentioned that the SPARCS is to be put into orbit in 2 years, in 2023, but you didn't mention what is the situation with the UV scope now?
Oh, sure. So UV scope is in development and to be proposed. So it's not funded. SPARCS is already funded.
No,
but
UV scope is
UV
in
scope-
phase A, I mean, or phase B.
No, not phase B. It's just going to be proposed in this upcoming mid-X proposal round. So, so we are working towards putting together the proposal to be submitted to NASA in December as part of the mid-X program. So if all works out, it would be 2028, right? But you know, it's not funded yet.
Okay, and one question relates to how to say, to forecast of the extreme ultraviolet flux. You need to estimate this flux because that's the evaporation of atmosphere is very important, but it's mostly due to extreme ultraviolet flux. But
Right.
from observations, you could get only some flux in more or less far UV. Of course, near UV and far UV, but you should forecast what will be the intensity on the flux. And is it reliable? There are good models for this.
Yeah, well, we are building, let me see if I have a plot specifically to that point. Let's see. So for instance, okay, let's see, maybe this plot will do it. Okay, so I didn't show this just in my backup plots, but what I'm showing you here are the observations, right? Far UV and near UV. And we will be observing all these emission lines and the formation temperatures of these formation lines. Many of them overlap with the formation temperatures of the EUV emission. So this slide is out of date already, but what you'll see is that we are actually building the temperature column mass structure of the star, right? Of the upper atmosphere of the star. And you can see, again, this is the work of Sarah Peacock and Travis Barman primarily, but you can see the photosphere here, right? And then we can by matching the spectra, can build up what the chromosphere, the transition region, and the corona are doing. And so, yes, I mean, it seems to be working, and it is, I mean, it's working, and we have it for a few M stars already published, and now we're working our way into building up a K component, because it's amazing how people have not needed this information yet, and now we need it, right? So anyway, I encourage you to read these papers. But yes, these papers by Peacock et al. And in there we go through the analysis and the reliability of them. But these are not just scaling relations. The scaling relations are not good enough in order to understand the planet atmosphere. There's too much uncertainty. And so this is a more physically motivated theoretical version of that.
Yeah, so I had a comment on that. You know, if you, so for example, on for the sun, there's some empirical, but it's tested over 50 or 60 years of observations, measure of the EUV flux through the so-called F10.7 index, which is a radio continuum in F10 point or at 10.7 centimeters. And there's in fact, there's a huge Canadian, you know, sort of Canada stamped activity started after World War II. And that's extremely well correlated. So, you know, it might be useful to look at sort of lower wave or higher, longer wavelength surrogates for the EUV. And that sometimes there's some nice little coincidences. So for example, if you want to know the Lyman beta radiation from the sun, which is difficult to measure because, you know, it's 1025 angstroms, but in the HST orbit, the resonance of oxygen, the triplet, it so happens that oxygen and Lyman beta are Bowen fluorescent with each other. So the bright oxygen lines you see, very easy to measure because they're at 1304 to 1306 angstroms. is a direct trace of the amount of Lyman beta that is produced in the sun.
Mhm.
So you may want to sort of look around and see if there are such nice, as a cross check, because
Right.
so the
Well, these
oxygen.
models have been validated against the sun for sure, right? They have. Are you talking? You're talking specifically about the Peacock models, right?
Yeah, I don't know. I'm not familiar. I was just generally making a general comment of using other little clever tracers
Yeah.
where, and you giving two examples from the sun.
Right. Okay. Thank you. I know about the F10. It's a lot of good.
Well, you grew up in Canada, you have to know. That's like,
I actually didn't learn about it then. I learned about it afterwards.
Fiona has another question.
Yeah, so this is a sort of programmatic question, so I apologize to the people for whom it's not interesting, but I'm kind of curious about your experience with the CubeSat small sat program through APRA. You know, what kind of flexibility do you have in terms of, if any, in terms of choosing orbit or launch date, or
Right.
you know, how's it working?
Well, we don't have much. We apply to the CSLI, the CubeSat Launch Initiative, and we state the orbits that we want, the orbit that we want, and what we will tolerate based on our design. We can't take every orbit, right? We can't take just any orbit, but we have some range of possibilities for which, because of thermal issues, because of time monitoring, like we don't want too many Earth eclipses to interrupt our observations the way HST does. So we don't have, we'll see exactly what we get, but we propose for a particular orbit. And then I think they try their best if possible. And then we can say something like, okay, we're willing as a project to wait 3 months, put our CubeSat on a shelf and we'll wait. And if nothing happens, if we don't get the sun synchronous orbit that we want, then we'll take a lesser orbit and our science will take a hit. So it depends so we don't have a ton of say, but we can at least request and wait to see what the opportunities are. I think sun-sync orbits, launches to sun-sync orbits are increasing for other reasons. And so I remain hopeful, but if we have to go to something else, we will, because you can't sit on a shelf forever.
So, and a follow-up question, just one of our scientific staff, Brian, who's on the call, actually is thinking about a X-ray CubeSat for monitoring of black hole binaries. But at any rate, what's your experience with the spacecraft bus? Did you go to a commercial vendor, or is JPL building it? Is it readily available and actually a reality, or what's the story there?
Yes, no, we are not building it ourselves. It's a commercial bus. There's a few companies that we put RFIs and RFQs out for. So I'm happy, Brian, if you want to reach out to me, I'm happy to share some names of companies depending on your requirements. And the biggest challenge is pointing requirements for us. So for astrophysics, you need better pointing than say for Earth observing, of course. And so there's different companies that have different options and capabilities. Let's put it that way. And so I'm happy, Brian, if you reach out to share my experience with different companies, if you like.
Yeah, and I'd also be interested just to hear how the interface with JPL was. I know that they've been a little, their small sat division thinks you can do a lot of really good stuff, and I know the rest of JPL is a little more skeptical about buses. But yeah, that'd be great.
Okay,
Yeah,
any other questions?
Mhm.
Well, if not, sorry, Brian, didn't mean to cut off. Maybe you want to just, since this is being recorded, I thought I'd spare you some embarrassment. I know you can talk to Evgenya directly.
Yeah, we should talk later. Happy to chat.
Yeah. Any other questions? So I just want to inform people that the UV Club has 4 more talks, and then we wrap up. Okay, so in fact, the last talk of the series would be led by Fiona Harrison and company on also responding to the competition that Evgenia talked about, which is December 9th, is, I suspect, a date very well known to both Evgenia and Fiona. So we'll end with that, but we have a talk on cost by the PI of the COS. That should be very interesting. Another small satellite mission from ASU also. Vargas will be giving a talk. Okay, so please check the UV Club web pages. Okay, bye everyone.
Bye, thank you. Take
Bye.
care.
Bye-bye.